Hello, welcome back. We are on Lecture 8 in Fundamentals of Inorganic Glasses. This corresponds to the first part of Chapter 4. Chapter 4 has to deal with microstructure in glasses. Now, most of the glasses that we are familiar with and that we use in our everyday lives tend to be homogeneous, meaning that they've got the same chemical composition throughout and therefore the same properties throughout. However, what we'll see in Chapter 4 is that there are a couple of ways for glasses to become inhomogeneous. And one of them that we're going to deal with today is through liquid-liquid phase separation. This is the first of two lectures on Chapter 4. Next time, we will deal with crystallization in glass and give an overview of glass ceramics. So today is liquid-liquid phase separation, and next time will be glass ceramics. So what we're going to cover today is first we're going to do the thermodynamics of mixing. This gives us the thermodynamic driving force for why liquid-liquid phase separation happens. Then we're going to cover what is liquid immiscibility and two different types of phase separation by droplet nucleation and by spinondal decomposition. And I'll show you how those different microstructures form, what they look like, and qualitatively, what are some of the kinetics of the evolution of these microstructures. So let us start with thermodynamics of mixing. Let's assume that we have two different components, A and B, that are mixed in our glass forming system. So if we've got A and B and they are being held at some temperature T and pressure P, and they are going to yield a solution. The question becomes, what happens to the solution of A and B when they are mixed together? And there are three different options for that broadly. The first option is that they could stay unmixed. In other words, they could remain no more than a physical mixture of A and B. The classic example of this would be trying to mix together water and oil. Water very much prefers to bond to other water. Oil prefers to bond to other oil, and so they stay unmixed when you attempt to mix them together. So that's the first option. The second option is that they could mix on an atomic scale and form a complete solution of A and B. This would be if you have a nice homogeneous solution of A and B to have something that is chemically homogeneous throughout the solution. And then the third option is that they could partially mix. In other words, they could mix in preferential ratios to form various compounds of A and B. And this is another type of liquid-liquid immiscibility, in addition to this first option of remaining unmixed. So what is it about the thermodynamics that governs which of these three options will take place? The degree of mixing depends on the Gibbs free energy of the mixed state versus the unmixed state. So if we consider before mixing here on the left, let's suppose that you've got some bottle of A here on the left and some bottle of B. And then what we're going to do is take that bottle of A and that bottle of B, and we're going to pour them together into the same vessel. And so what happens to the Gibbs free energy of the system as a result of that mixing? In order to get this Gibbs free energy of mixing, we need to calculate the Gibbs free energy before mixing and then compare it to the Gibbs free energy after mixing. Now, before mixing, if we've got separated subsystems of A and B, let's assume that we've got a mole fraction here, where this little c corresponds to the mole fraction of B, and therefore the mole fraction of A would be 1 minus c, such that if you add up those two mole fractions, they will add up to 1. And let's suppose also that we have a Gibbs free energy of the unmixed B state, that is this G sub B, and we have a Gibbs free energy of the A state that is unmixed, which is this G sub A. And if we've got little c mole fraction of B and 1 minus c mole fraction of A, then the total free energy of the system is just this weighted average of the two, where the weighting factors are the mole fractions of the two different phases there. And therefore, we can write the Gibbs free energy of this unmixed system as G1, 1 meaning the state before mixing occurs, and that's just equal to 1 minus C times GA plus C times GB. Now, as a result of mixing, normally what we do is we represent the change of Gibbs free energy as a result of mixing by delta G sub M. So in this case, we can represent the Gibbs free energy of the system after mixing by G2, and this would be equal to the Gibbs free energy of the unmixed system, G1, plus the change of Gibbs free energy due to mixing, delta G sub M. So G2 equals G1 plus delta G sub M. And now the question becomes, what is the sign of delta G sub M? If this Gibbs free energy of mixing, delta G sub M, is positive, then that means that the system will remain phase separated. If the delta G sub M is negative, then that means there is some thermodynamic advantage to having some degree of mixing in the system. And so if this delta G sub M is negative for a certain range of compositions, then mixing will take place in that range. Let's take a closer look then at this free energy of mixing, since this is the key parameter that governs the degree of mixing of our solution. Now, what we want to do is if we have a Gibbs free energy, we want to break that into enthalpic and entropic components. So the free energy of mixing, delta G sub M, is equal to this enthalpy of mixing, or heat of mixing, delta H sub M, minus the absolute temperature T times the entropy of mixing, delta S sub M. Now, if we have a two-component system, if it's just a normal solution here, the entropy of mixing in that two-component system, delta S sub M, would be equal to minus the gas constant times the mole fraction of one of the species times the natural logarithm of its mole fraction, plus the mole fraction of the other phase times the natural log of that mole fraction. So we just take all of the mole fractions of each of our phases that we are mixing together, and it's that mole fraction times the logarithm of that mole fraction, and then you add these up for all the different phases. And this is just the standard Gibbs formula for the entropy of mixing. Now, what is the sign of the entropy of mixing? You see that we've got a minus sign out in front, but what do we know about all of the molar fractions here? All of these molar fractions are less than 1. So if you take the logarithm, the natural logarithm here of a number that is less than 1, that means that the natural logarithms are going to be negative. So we've got negative values multiplied by this minus sign, which means that the entropy of mixing is always going to be a positive quantity. And therefore, entropy always increases upon mixing. What this means is that if everything were left up to entropy, mixing would always be preferred because the number of possible mixed states so greatly exceeds the number of possible unmixed states. And therefore, the entropy of mixing says that mixing should be preferred. The more interesting part actually comes in with this enthalpy of mixing or heat of mixing, delta H sub M, because that can be either positive or negative. So let's consider the various types of solutions that we may encounter. The simplest type of solution is an ideal solution. When there is an ideal solution, there's no bond energies that matter in the system, and therefore the enthalpy of mixing here, delta H sub M, is equal to 0. And if that's the case, then our Gibbs free energy of mixing is entirely dominated by the entropy of mixing, and it is negative at all temperatures. Because if we look at our formula here, for an ideal solution, if the heat of mixing here is 0, then we've got minus the absolute temperature times the entropy of mixing. We know that the entropy of mixing is always positive, the temperature is always positive, and therefore with a minus sign out in front, this means that the Gibbs free energy of mixing for an ideal solution will always be negative. And that means that the system will be thermodynamically preferred to mix regardless of the different molar fractions of the different phases in your system. So that is a very simple case, and that always favors mixing. So we would be unable to get any type of immiscibility for an ideal solution. Now, the more interesting case, and the case that we're going to deal with for most of this lecture is a regular solution. And according to the regular solution model, the enthalpy of mixing is not equal to zero. It could be positive or it could be negative, but it's not equal to zero. And then the entropy of mixing is just given by the Gibbs formula from the previous slide. There's also more complicated cases of non-regular solutions. With non-regular solutions, the enthalpy of mixing is non-zero, and the entropy of mixing is given by some more complicated formula. But for today, what we're going to deal with is regular solutions. So in this context of regular solutions, we can describe the heat of mixing, or this enthalpy of mixing, by a formula as shown here, which is symmetric about the molar fraction equal to 1/2. So one of the ways that we can write the heat of mixing is delta H sub m is equal to some factor here, alpha, which is called the excess interaction energy, times the mole fraction of one phase times the mole fraction of the other phase. So it would be alpha times C times 1 minus C. And the key parameter here is this alpha, the excess interaction energy. This is, or can be given by Avogadro's number, which is going to convert our individual bond energies to some molar energy, times our coordination number, which tells us the number of bonds. And then the key part here is in the middle of these square brackets, and it's based on a difference of the bond energies between the bond energy of the mixed bonding type. So this would be the bond energy between an A and B bond. So this would be bonding between A and B, minus the average of the bond energies between the like species. So if you've got a bunch of A atoms and a bunch of B atoms, the question is, do the A atoms prefer to bond to other A atoms, and the B atoms prefer to bond to other B atoms, or do they prefer to bond to the unlike type, to A and B? And the way to consider that is, what is the average bond energy between the bonding of the like types versus the bond energy between the unlike types? And whether this is positive or negative will tell you whether the enthalpy of mixing is positive or negative. So if the bonding between unlike types, AB, is preferred, then that means that this delta H sub m will be negative, and that is going to favor mixing from an enthalpic point of view. On the other hand, if the average of the bond energies between the like types is preferred, then the delta H sub m is going to be positive, and that means from an enthalpy point of view that the system would prefer to stay unmixed. So what are some possibilities here? What we can do is actually make a plot that shows the different contributions to the Gibbs free energy of mixing as a function of this molar concentration, or this mole fraction here, C. This mole fraction C goes from 0 to 1. You'll note here that this left vertical axis is labeled as A. That's because C is the mole fraction of B. So if C is equal to 0, that means the system is entirely composed of this A phase. On the other hand, on this right-hand axis, this right-hand vertical axis, this is labeled as B because if the mole fraction of B is equal to 1, then the system is entirely in the B phase. So, and then what we have on this axis are the enthalpy of mixing, the entropic contribution to mixing, which is minus the temperature times the entropy of mixing. And then if you add those two curves together, what you get is the Gibbs free energy of mixing. Now, all of these curves go through 0 at both the left vertical and the right vertical axes, because those two endpoints correspond to the pure phases A and B. So mixing is not possible if you've got the pure phases A and B, but if you're anywhere in between these end members, then the question becomes, what is the thermodynamic advantage of mixing? Now, this left-hand plot shows the case where what if the enthalpy of mixing, delta H sub m, is negative? This means that the bonding between A and B would be preferred compared to the average bonding between A and B. So what this means is that if you take A and you take B and you mix them together, they will want to bond to each other, and the system is going to give off heat upon mixing. And this is what's called an exothermic reaction upon mixing, because heat is given off. That means that the delta H sub m is negative, and it is going to be symmetric about this C equals 1/2, according to the formula here on the previous slide. So that the shape of that curve corresponds to C times 1 minus C. And if you plot that, it has the shape here shown by delta H sub m. Now, the next part here is the entropy of mixing. The entropy of mixing is given by our Gibbs formula. This is also symmetric about C equals 1/2, but the shape is somewhat different because of the natural logarithms in this formula. And we know that the minus T times delta S sub m is always going to be negative because the entropy of mixing is always positive, the absolute temperature T is always positive, and there's a minus sign out in front. So this means that the entropic contribution to the Gibbs free energy of mixing is also negative. So on this left-hand plot, enthalpy says, yes, I want the system to mix. It is thermodynamically advantaged from an enthalpy point of view for the system to mix. From an entropy point of view, the system always wants to mix. So the enthalpy of mixing and the entropy of mixing are both in agreement. They both are going to favor mixing of the system. And if you add these two curves together, then you get the total Gibbs free energy of mixing, which is negative across all of this concentration space. So this left-hand side here is easy. This is telling us that for any value of C, we can minimize the Gibbs free energy of the system by having a complete mixture of A and B, regardless of what the concentration is. So on this left-hand side, mixing is always thermodynamically preferred. Now, the situation becomes a bit more interesting on the right-hand plot. On this curve, what we've done is we flipped the sign of the heat of mixing. So now the delta H sub m is positive instead of negative. And what this is telling us here is that from purely a bond enthalpy point of view, the A and the A prefer to be bonded to each other, and the B and B prefer to be bonded to each other instead of having the mixed bonding between A and B. So if you take a bottle of A and a bottle of B and you mix them together, the enthalpy of mixing, this heat of mixing, is positive. This means that the mixing is endothermic, which means it's going to take in heat from the surroundings in order to enable the mixture to happen. And now the other thing is that we've got a competition now between the enthalpic term, the delta H sub m, which says that this is thermodynamically unfavorable to mix, and the entropy, of course, always favors mixing. And so enthalpy says that the system does not want to mix. Entropy says that the system does want to mix. Which one of these wins? When you add up the delta H sub m and then minus T delta S sub m, that gives you the delta G sub m, the Gibbs free energy of mixing. And in the case that I've drawn here, you can see that the entropic part is dominant over the enthalpic part, such that the delta G sub m, the Gibbs free energy of mixing, is negative across this entire concentration space and has just a single minimum here at C equals 1/2. What is the key parameter that governs whether the entropy is dominant or the enthalpy is dominant? It is the temperature of the system. This temperature of the system here, T, is the weighting factor on the entropy. So if the temperature is high, the thermodynamics of the system always favors entropy. High temperature always favors entropy. Low temperature will always favor enthalpy. So in this case, we are at a high enough temperature where the entropic part is large enough to overwhelm the enthalpic part, and the system will still want to mix despite the penalty that it has to pay in terms of the enthalpy of mixing. But what happens now if we take this temperature T and we gradually lower it? As we gradually lower the temperature, this entropy curve is going to keep shifting up and up and up. And eventually there's going to be some closer competition between the enthalpy of mixing and the entropy of mixing. And when that happens, when they become of similar order to each other, we start to see this single minimum of the Gibbs free energy actually divide up into two minima. And the reason is that the shapes of the delta H sub m and the delta S sub m curves are different. The delta H sub m curve has the shape of the C times C1 minus C, and the enthalpy curve has these natural logarithms in it. And because of the different shapes of the curve, there's different curvatures there. When you add the H sub m curve and the minus T delta S sub m curve, you can get a Gibbs free energy of mixing curve that no longer has a single minimum at C equals 1/2, but it divides into two minima. And those two minima in this case are given by the locations here, little a and little b. And this suddenly becomes a lot more interesting from a thermodynamic point of view, because what if you have if you've got a mole fraction that is C equals 1/2? If you've got a mole fraction of C equals 1/2, if you had a completely mixed system where there's complete mixing at the atomic level, the delta G sub m would tell you that it's overall negative, that mixing is preferred compared to unmixing, but it would be at this point that I'm showing here with my pointer. And that does not correspond to the minimum Gibbs free energy. The minimum Gibbs free energy for this concentration would actually fall on this tie line that connects these two minima. And so this is an example of having some degree of liquid-liquid immiscibility. In other words, the solution is not completely mixed at the atomic scale, but it prefers to phase separate into compounds. One of those compounds having a concentration that corresponds to this little a. So this would be enriched in this big A, and then have some amount of this big B in it. So this is one of the phases, little a, and this has a Gibbs free energy that corresponds to this G sub A. And then the other phase, that is this preferential compound, corresponds to the other minimum. And that has this concentration here of little b. And the Gibbs free energy that corresponds to that is G sub E. So if we are at any concentration in between these two minima, so in between the little a and the little b, the lowest Gibbs free energy of the system is not made by following this complete mixing line here for the Gibbs free energy of mixing. Rather, the minimum in the Gibbs free energy is obtained by drawing a tie line between the two minima. So between the Gibbs free energy of the little a phase and the Gibbs free energy of the little b phase. So instead of having the C equals 1/2 here, where there's a complete mixture, the Gibbs free energy of the system can be lowered if it phase separates into the little a phase and the little b phase, in which case the Gibbs free energy would be lower. It would be on this dashed line, this tie line, instead of being on the solid line up here. So what this means is that because of this competition between the enthalpy of mixing, which in this case is positive, so from an enthalpy point of view, mixing is not preferred, and the entropy of mixing, which always favors mixing, our single minimum has split into two minima, and when that happens, some degree of phase separation is favored for any of the concentrations that fall between the two minima. If the system is outside of that range, if it's outside of this range between the two minima, then the system will favor mixing, because in that case, if you're between this 0 and this GA here, the minimum in Gibbs free energy corresponds to the completely mixed system on the left-hand side. And also on the right-hand side, if you were to the right of this little b phase, then the minimum in Gibbs free energy comes by having a complete mixture following the solid line. So what this means is that miscibility, or complete mixing, is favored outside of the range of those two minima. But if the system is in between the two minima, then some degree of phase separation will take place. So what I was showing there was at a particular temperature of T equal to T1. And this phase diagram that I'm showing on this slide now has temperature on the y-axis. The temperature that we were at on the previous diagram is shown as T equals T1. And I've got a dashed line here that goes horizontally across. And this immiscibility dome here, this solid curve shown here, corresponds to the locations of all those minima in the Gibbs free energy. So if we look at this temperature of T equals T1, on this diagram, those minima occurred in this preferential ratios of a little a phase and a little b phase. And on this diagram on slide 10, you'll see that the locations of this immiscibility dome correspond to those same molar ratios. So here, this dashed line is passing through the immiscibility dome at 2 points. If you drop this down to the horizontal axis, the first minimum occurs at this little a phase. The second minimum occurs at this little b phase. Now, this is for this particular temperature T1. What happens if we increase the temperature of the system? If you increase the temperature of the system, those two minima are going to become closer and closer together until they eventually merge. So as we take the system and we increase the temperature of the system, that is going to lower this entropic curve on this plot. This entropic curve is going to get lower and lower. That means that entropy is gradually going to become more powerful compared to enthalpy. And that's going to pull these two minima closer and closer together until they get to a point where there's a single minimum on this diagram. And that is what is being shown by this immiscibility dome here, is that these locations of the minima, if we start off at T1 and increase the temperature, those locations of the minima are coming closer and closer together. So as we go up in temperature, the two ends of the dome are becoming closer and closer together until those two minima merge into a single minimum. And the temperature at which that occurs is labeled as Tc. This is called the critical temperature, also called the upper consulate temperature. The upper consulate temperature is the temperature above which the system is single-phased for all compositions. So at any temperature above the critical temperature, this means that entropy wins completely at all temperatures at and above Tc. This means that a homogeneous liquid is favored. Phase separation, or immiscibility, is only favored when you are within this immiscibility dome. So if the system drops below T sub c, if you are at any location on this diagram within the dome, then phase separation will be favored, and the system will want to demix into compounds that are on either side of the dome. So for example, at this temperature T1, if you are at any concentration in between little a and little b, so anywhere within this immiscibility dome, the Gibbs free energy of the system can be minimized by having that system phase separate into this little a phase and the little b phase at the boundaries of this immiscibility dome. On the other hand, if you are outside of the immiscibility dome, say in this region on the right or in this region on the left, then the system is still favored to be miscible. It's still favored to mix at the atomic scale outside of that immiscibility dome. And the bounds of this immiscibility dome become broader and broader as the temperature of the system is lowered, because as the temperature of the system is lowered, enthalpy becomes more and more dominant, and therefore a greater range of compositions are thermodynamically favored to mix. And so this is one of the key quantities here, this immiscibility dome. And what we see, however, is that there's actually another dome inside the immiscibility dome, which is called the spinodal dome. And on the upper right-hand part of this plot, you'll see the immiscibility dome drawn by the solid line. And within that, there is a second dome called the spinodal dome, and that is given by these dashed lines. And what this is telling us is that there's actually two different types of liquid-liquid phase separation that can occur, depending upon whether you are within this spinodal dome, in which case something called spinodal decomposition occurs, or if you are within the immiscibility dome, but outside of the spinodal dome, in which case another type of phase separation occurs called droplet nucleation and growth. So to determine the boundaries of these two domes, what we need to do is look at how the Gibbs free energy of mixing is evolving as a function of concentration C. So what we have here is in the second plot, this shows the Gibbs free energy of the system at this particular temperature T1. And you can see, as we had before, the boundaries of the immiscibility dome here occur at the little a phase and the little b phase. And if you drop this down to the Gibbs free energy curve, you'll see that the little a phase has a minimum in Gibbs free energy, and the little b phase has a minimum in Gibbs free energy. The next curve down is the first derivative of the Gibbs free energy with respect to concentration. And obviously, if these correspond to minima in Gibbs free energy, that means that the slope of the Gibbs free energy curve, or this first derivative of Gibbs free energy with respect to concentration, is zero at both the A phase and the B phase. So this is what gives us the boundaries of the immiscibility dome. The boundaries of the immiscibility dome correspond to the locations of the minima of the Gibbs free energy. In order to get the boundaries of the spinodal dome inside the immiscibility dome, let's take a look at what we have here. You've got the location here of the spinodal dome. And if we drop this down, these are at locations D and E. This actually corresponds to an inflection point in the Gibbs free energy as a function of concentration. There is an inflection point here on the left and an inflection point here on the right. And those inflection points correspond to the boundaries of the spinodal dome. And what this means is that if we drop this down to the first derivative, this first inflection point is actually a maximum in the first derivative. The second inflection point is a minimum. And because they are inflection points, the curvature is zero, which means if we take the second derivative of the Gibbs free energy with respect to concentration, those second derivatives will be zero at the boundaries of the spinodal dome. And indeed, this is what you can see at these points D and E. These correspond to a zero in the second derivative of the Gibbs free energy with respect to concentration. And so if we follow this all the way up, you see that the way that we get the boundaries of the spinodal dome is by seeing where the inflection points are on this Gibbs free energy curve, or in other words, where the second derivatives become zero. What this means is that within the spinodal dome, say between these two boundaries here, between these two inflection points, note that the curvature is negative. This curvature is negative because the Gibbs free energy curve is curved downward. And you can see that if you drop down to the second derivative here between points D and E is in fact negative. So this is a negative curvature. And that negative curvature is the key parameter that characterizes spinodal decomposition. What we're going to see is that this negative curvature means that the system is actually unstable with respect to little fluctuations of concentration. And I will show you that on the next slide. But the next thing to note here is that within the immiscibility dome, outside of the spinodal dome, what is the curvature? Here, so let's say between the point A and the point D, the curvature here is positive. And you can see on the second derivative plot, indeed, the curvature is positive. Likewise, between the points E and B, the curvature here is positive, meaning that the second derivative is positive. So droplet nucleation, which is the type of phase separation that occurs within the immiscibility dome, but outside of the spinodal dome, is characterized by a positive curvature. What do these look like in terms of the microstructure of the glasses? Droplet of phase separation looks like the left-hand plot. And this actually shows some droplet phase separation in soda-lime silicate glass. And you can see that there is one phase that is the dominant phase, and that is the matrix phase. So most of the system is in the matrix phase, but within that matrix phase, there are droplets that form. These droplets have a different concentration of species within the droplets. You'll see that they are largely spherical or close to being spherical. You will also see that there are sharp boundaries between the droplet phases and the matrix phases. The other type of phase separation that occurs within the spinodal dome is called spinodal decomposition. And with spinodal decomposition, you don't have a matrix phase anymore because you don't have one phase that is the dominant one. Instead, you have two different phases that are similar in concentration to each other, and they form kind of this interconnected, almost like a worm type of microstructure, where you've got two interpenetrating phases where one is not really dominant over the other. This is an example of spinodal decomposition, and this is occurring in a glass called Vicor glass, which was designed to give this particular type of spinodal decomposition as phase separation. Why is it that this occurs? This all has to do with the relative stability or instability of the system with respect to minor concentration fluctuations, and what is the role of the second derivative in telling you whether the system is going to be stable or unstable. So the way that we can analyze this is consider that the system has some average concentration here, this average of C, but there are little fluctuations that occur locally because of thermal vibrations of the system. And so there are local concentration fluctuations. So if we denote the average concentration as being C within angle brackets, and then the localized fluctuations are this little delta C, the Gibbs free energy as a result of that fluctuation with respect to the average can be given by a Taylor series expansion. So this is the Gibbs free energy, including the concentration fluctuation. Using a Taylor series expansion, we can write that this is equal to the Gibbs free energy of the average concentration, plus then the concentration fluctuation delta C times the first derivative evaluated at C equals the average concentration, plus then 1 over 2 factorial, so 1/2, times the fluctuation squared times the second derivative plus ... And if you continue this Taylor series expansion, there would be the third derivative term, the fourth derivative term, and so on. But the reason we use Taylor series expansions is that we will truncate this after a certain number of terms. And so we're going to truncate this after the quadratic term, so after the second order term here. And what else do we know about these concentration fluctuations is that they are just as likely to be positive as they are to be negative. And so in an average sense, this delta C here is going to be positive just as much as it is negative. And in an average sense, then the contribution from this first derivative term is going to be 0. So this linear term actually goes away. But in this quadratic term, the fluctuation is squared. And what this means is that whether or not the delta C is positive or negative, when you square it, that's going to give you a positive number. And so this second order term here is actually the most important term because this is always positive. And if the delta C squared is always positive, and then what is the contribution then to the Gibbs free energy as a result of the concentration fluctuation? Is it going to be a positive contribution to the Gibbs free energy, or is it going to be a negative contribution? And since this delta C squared is always positive, then the sign of the change of the Gibbs free energy is entirely determined by the sign of the second derivative of the Gibbs free energy with respect to concentration. And so we can write this, we can approximate then the Gibbs free energy of the system, including the concentration fluctuation, as being equal to the Gibbs free energy of the average concentration, plus then this quadratic term, 1/2 delta C squared times the second derivative. And if the second derivative is positive, we know that's droplet nucleation, because we know then that the system is stable with respect to these small fluctuations, because the small fluctuation is going to act to increase the Gibbs free energy of the system. On the other hand, if the sign of the second derivative is negative, then the system is thermodynamically unstable with respect to those small fluctuations, because every little small fluctuation is going to lead to a lowering of the Gibbs free energy of the system. And so this negative curvature here, this negative second derivative, gives us spinodal decomposition. And that is exactly what we saw in this diagram here. Within this spinodal dome, the second derivative is negative, which means that spinodal decomposition happens within that spinodal dome because of the negative curvature. On the other hand, where we have positive curvature inside the immiscibility dome, this is where we have droplet nucleation, because the system is stable with respect to minor fluctuations. What this means is that for this droplet phase separation, there's always a very well-defined boundary between the two phases because of this local stability with respect to those fluctuations. Whereas with spinodal decomposition, the phase separation kind of gradually emerges as this continual process by having a rather diffuse boundary between the two different phases. And that's because of the lack of stability with respect to minor fluctuations. So if we consider now kind of a cartoon version of the evolution of phase separation in the droplet nucleation case on the left versus spinodal decomposition on the right, we can see how this evolves over time. So these diagrams both show kind of a schematic picture of how the concentrations evolve with increasing time, where we start with our initial concentrations on top, and then time is increasing going in the downward direction. Now, what happens on, let's start off on the right with spinodal decomposition, is if we've got some initial concentration labeled here as M, where this is approximately in the middle or close to being in the middle between the two phases A and B. The little a and the little b are the boundaries of the immiscibility dome, as we've shown. And there are going to be random compositional fluctuations that occur as a result of thermal vibrations of the system. And the system is unstable with respect to those vibrations because of the negative sign of the Gibbs free energy. And what this means is that gradually phase separation starts to form, where some of our B is going to migrate into a B enriched phase. That's going to leave behind a B depleted phase that is enriched with A. And so you'll get this microstructure that starts to form where certain regions become enriched in B, other regions become depleted in B. Over time, they will tend to approach closer and closer to the little b and the little a concentrations, but the boundaries between them are diffuse, and they only become sharp boundaries when the phase separation itself has completed. And so when the phases actually reach their target of little b and little a, then and only then do you have the sharp boundaries that form between the phases. So the spinodal decomposition is a gradual process where you start off with diffuse boundaries between the two phases, and then they sharpen over time. On the other hand, with droplet nucleation, we're starting at a concentration here, M, which is not really in the middle, but a lot closer to one of the phases compared to the other one. Whichever phase that it is closer to becomes the matrix phase, because there is more of that in the system. Whichever phase that it is farther away from becomes the droplet phase. So in this case, we've got the capital M, and this is close by this A phase. So the A phase becomes the matrix phase. And within that matrix phase, we nucleate and grow droplets of the B phase. And you can see that over time, we've got evolution of B, or this migration of B into droplets. Even when small droplets form, there's a very sharp boundary between the droplet phase here and the matrix phase. Over time, more and more of the B will cross the interface from the matrix to the droplet, and that causes the droplets to grow. And the interface is going to stay sharp between the droplet phase and the matrix phase as the droplets grow. And then the droplets will stop growing when the matrix phase has completely achieved its target concentration here of A. And the reason for the sharp interface is because of the relative stability of the thermodynamics of the system with respect to these small fluctuations because of the positive sign of the curvature of the Gibbs free energy of the system. So these are kind of two qualitative evolutions of phase separation for droplet nucleation versus spinodal decomposition. To say it again in words, droplet nucleation and growth is governed by an invariance of the second phase composition with time at constant temperature, meaning that the droplet phase always has the same composition. And it's really the concentration of the matrix phase that is evolving as the droplets are growing. The interface between the phases is always sharp during growth. There's also a tendency for random distributions of particle sizes and positions of the droplets. And there's a tendency for separation of second phase spherical particles with low conductivity. So you don't get much connectivity between the droplets in droplet nucleation and growth. On the other hand, with spinodal decomposition, we have a continuous variation of both extremes in composition with time until the equilibrium compositions are reached. There is an initially very diffuse interface between the phases, which sharpens up over time. And there is a tendency towards regularity of second phase distribution in size and positions, characterized by kind of a characteristic geometric spacing. And there's a tendency for separation of second phase non-spherical, very elongated types of phases with a high degree of connectivity. Now, phase separation can be very interesting if you change the temperature of the system too, because as we've seen, as you lower the temperature of the system down, the boundaries of the immiscibility dome and the spinodal dome change. These domes become broader and broader, and that means that phase separation can occur in different steps. And what I'm going to show you is an example of that in a system that has barium oxide, boron oxide, and silica, where it is actually cooled from above TC, above the critical temperature, downward. And it's easier to see in this diagram here, where what we do is we start off above the critical temperature, so above the maximum temperature of this dome, and some homogeneous melt phase here, X. Now, this wants to stay homogeneous. It wants to stay fully mixed until it drops into the immiscibility dome at some point. When it drops into the immiscibility dome, if it's held at this first temperature here, T1, this will want to phase separate into a matrix phase here that it's closer to, which is M1, and then a droplet phase. So this gives us some initial phase separation into a matrix here, and then the droplet within that matrix. If now the temperature is lowered, this matrix phase composition actually falls within the immiscibility dome again. And so this matrix will want to phase separate again into a new matrix phase, M2, and then a new droplet phase here, TR2. And then likewise with the droplet, if you drop this down, the droplet is going to want to phase separate into a matrix phase and a droplet phase, and so on. And this is exactly what you can see here in this microstructure on the right, is that on the left, is that there is an initial phase separation that occurs by forming these initial droplets here inside this matrix phase. Within the matrix, as this is lowered, the matrix phase wants to phase separate into a new matrix and then new droplets within that matrix. Likewise, within the initial droplet phase, when this initial droplet phase cools down, it's going to be within the immiscibility dome again, and that will want to phase separate into a matrix and a new set of droplets. Now, those new droplets, when they cool down, they will again fall into the immiscibility dome, and these droplets will want to phase separate into another new matrix phase with new droplets. And so we've got droplets within droplets within droplets and each one of them is within a different matrix phase at each one of those scales. So you can get some very interesting microstructures that can evolve depending upon the temperature path that you put the system through and how much time that you spend at each temperature, and whether you give the system enough time to observe the phase separation or not depends on the kinetics of the phase separation process and your heat treatment schedule. Now, where is this used? A classic example of spinodal decomposition occurs in glasses that are called opal glasses. They are called opal glasses because of the white color, and you probably have some of these in your kitchen. This is an example of Corel, which is one of Corning's tableware products. So these are actually strengthened glass tableware products that correspond to laminated glass faces, where the interior glass is a phase-separated glass by spinodal decomposition. Using the microstructure here shown on the left, you can see the interpenetrating networks here, this lighter phase and then the darker phase. And so you've got two interconnected phases that make these interpenetrating networks, and that is characteristic of spinodal decomposition. You can see the length scale here is on the order of a micron, so the length scale is similar to the length scale of visible light. And because the refractive indices of these two different phases are different, that means that every time visible light tries to propagate through the system, every time it encounters an interface, it's going to scatter at that interface. And that is what gives this the white color, so that all the light is being scattered at these interfaces. So this makes the interior part of these glass plates, giving it the white color. There's a very thin layer of a cladding glass, which is actually a clear cladding glass that envelops this phase-separated glass. And that clear glass is designed to give the overall glass plate improved strength, improved chemical corrosion resistance, so it can perform really well if you drop it on the floor or if you put it in the dishwasher many times. So this phrase opal glass, this generally implies glasses that have spinodal decomposition, such as in Corel plates. And I want to finish with one of our glass greats. One of the people who developed the thermodynamics and kinetics of phase separation initially was the scientist John Kahn, who lived from 1928 through 2016. He was born in a Jewish family in Cologne in Germany, and obviously that was a terrible time to be Jewish in Germany. He and his family fled Nazi Germany in the 1930s and emigrated to the United States in 1939. Kahn served in the U.S. Army during World War II and became a U.S. citizen at the conclusion of the war in 1945. Following the war, he went to UC Berkeley, where he got his PhD in physical chemistry, and he had a very distinguished career at MIT and NIST after that, and became a leading authority on thermodynamics and kinetics of phase transformations of materials. And it was his pioneering work on phase separation that was critical for our understanding of everything that we covered today. So to summarize, initially homogeneous liquids can phase separate if that unmixing will lower the free energy of the system. Liquid-liquid phase separation can occur by droplet nucleation or spinodal decomposition, and that depends on the sign of the second derivative of the Gibbs free energy. All right, thank you everyone for listening. Please let me know if you have any questions. Next time, we will finish up chapter 4 by dealing with microstructural formation through controlled nucleation and crystallization, where we can turn glasses into glass ceramics. All right, thanks everyone. I will see you next time.